Welcome back. This is tutorial 24, still with drill 18, continuing on with receivers, but in particular we're going to be looking at Ssb receivers, which is a slight modification of the receiver that we last looked at in tutorial 23, which was the double conversion double sideband superheterodyne receiver. So stay with me and we'll have a look at the block diagram of that for Ssb, and we'll also be looking at the practical block diagram of a transceiver so that you can get the big picture, but you don't have to worry about being examined on that. And we'll also be going through your trial questions on receivers in this tutorial as well. If you've just done tutorial number 23, this block diagram should look very familiar to you because I've made very few changes to it. Let me just get something to point with. Before we had a double conversion superheterodyne receiver for double sideband, and now we've made some modifications to the circuit for single sideband. And the only extra stage that I've put in is this one here. Also what I've done, the beat frequency oscillator, also what I've done is I've changed the frequencies just to show you that the actual frequency of operation is not important. Here we're transmitting on single sideband. We've got a bandwidth of 0 to 3 kilohertz of voice frequencies going into our Ssb transmitter, and we're transmitting the upper sideband, which is 3 kilohertz wide, the same as the width of the voice frequencies. And our carrier, I've shown it as a dotted line to indicate that it's not there, but let you know where it would be. The carrier is on the bottom end of the upper sideband and the top end of the lower sideband, but we don't have a lower sideband. This is single sideband. We're only transmitting on 144 megahertz. The carrier would be here if it existed, and the upper sideband extends above 144 megahertz by 3 kilohertz for single sideband. The problem with demodulating an Ssb signal that we didn't have with a double sideband signal is that with a double sideband signal the carrier was transmitted. So when we fed the sidebands and the carrier into the demodulator or detector, the carrier was there already to mix with one of the sidebands to produce audio output, to reproduce our original audio. With single sideband, we have to have an oscillator reintroduce the carrier. That's why the tuning of single sideband receivers is a little bit more tricky than double sideband, because double sideband, the carrier is there and it's on the right frequency and it perfectly converts the sideband back to audio. With an Ssb receiver, we have a BFO, a beat frequency oscillator, which we have to adjust to be exactly the correct frequency that the carrier would be on if it still existed. If we're just 100 hertz out or a couple of 100 hertz out, our demodulated audio will sound a bit Donald Ducky, and hence the reason why Ssb sounds a bit Donald Ducky sometimes is because people haven't got their BFO adjusted to exactly the correct frequency. Let's have a look at the frequencies involved. We're transmitting on 144 megahertz, that's our carrier frequency. This is a double conversion receiver. There's one frequency converter, there's the other frequency converter. Our first IF is 10.7 megahertz, Notice the bandwidth is narrower now. It's plus or minus 1.5 kilohertz, the bandwidth of this IF amplifier. There would probably be a crystal filter in there, a crystal bandpass filter, giving us this narrow bandwidth of 3 kilohertz. The 10.7 megahertz high IF frequency will do away with any image interference problems we might have. That's why we're using such a high IF. And the second IF is still 455 kilohertz, but it's narrower now too. So really, when you change from single sideband to double sideband, you should be changing the filters, the crystal filters in one of the IF amplifiers. Most radio amateurs don't do that anymore because they don't use AM very much. They do use AM, but they don't use double sideband. The type of AM they use is single sideband, and a single sideband filter, crystal filter, is quite an expensive purchase, and that would be plugged into one of the IF amplifiers. So we have 144 megahertz coming in, and our local oscillator is on 154.7 megahertz. Now, to have an oscillator running at that frequency is asking for instability. We're not going to go into phase lock loop. Would love to, but it would just increase the time of your course, and it's not in your syllabus. So this oscillator would be a phased lock loop. That would give it stability on 154.7 megahertz. If we tried to make an LC oscillator, or even an ordinary crystal oscillator run at that frequency, we'd find we'd have lots of drift problems. As before, the difference between the incoming signal and the local oscillator, if you subtract 144 from 154.7 megahertz, you get 10.7 megahertz. So our wanted signal, exactly as before, is converted by the first frequency converter to the first IF of 10.7 megahertz. Then the second frequency converter, which is a crystal oscillator on 11.155 megahertz. If you look at the difference between 10.7 megahertz and 11.155 megahertz, you'll see that it's 455 kilohertz. So this frequency converter is converting the 10.7 megahertz single sideband signal to a single sideband signal on 455 kilohertz. Now, before, we had the carrier to mix or beat with the 455 kilohertz upper sideband signal. We don't have a carrier anymore, so we've now got to reintroduce the carrier with the BFO. So the BFO would be approximately on 455 kilohertz, which is where the carrier would be if it was still there. If I was to draw this single sideband signal coming out of this second IF amplifier, there we have our upper sideband, and it's no longer on the frequency it was transmitted on. It was transmitted on 144 megahertz, but the carrier, if it was there, would be just at the bottom of the upper sideband. So we need to adjust the BFO to be where the carrier would be if it was still there. Then the carrier can mix with the upper sideband, all of the frequencies in the upper sideband, to give us our original audio. And that's all the changes that are required for a single sideband receiver. We need a beat frequency oscillator. When we use a detector along with a BFO, there's really no change in the detector, but because it's being used in this way with a BFO, it is in fact a frequency changer again, same as the last three. So that's a frequency changer that changes 144 to 10.7. This is a frequency changer that changes 10.7 to 455. This is a frequency changer, and it changes 455 kilohertz to voice frequencies. So all we're really doing is changing frequencies, and we keep changing until with the last change we change it back to audio frequencies. When we do that, we give the detector a different name, just to make life hard. And it's no different than an ordinary detector, except it has a BFO going into it. And it's called a product detector. Now you need to remember that because you might be asked about product detectors. Product detectors are used for the detection of single sideband, and they also work for telegraphy as well. So that's a product detector. Should be labelled product detector if this was an Ssb receiver, but I wanted to leave it to show you the differences between the double sideband receiver and the Ssb receiver is really just the introduction of a beat frequency oscillator, and we call the detector a product detector. Everything else pretty much remains the same, except the bandwidth is sharper. The bandwidth is now only 3 kilohertz of the IF amplifiers, and to get such a sharp bandwidth we really need to use crystal filters in either one or both of these IF amplifiers. Now an SSB receiver is a telegraphy receiver as well. So suppose we were transmitting just a carrier, which is what Morse code is. We'll take away the upper sideband. So we're just transmitting a radio frequency carrier on 144 megahertz, and we're turning that carrier on and off in the pattern of the Morse code. That's what Morse code is. Morse code doesn't have any tone. The tone produced in the receiver is made by the receiver. Let's suppose we had just an unmodulated 144 megahertz signal transmitting Morse code by being switched on and off. It's a radio frequency signal being switched on and off coming into this receiver. It would be amplified. It's converted to 10.7 megahertz and amplified again. It's converted to 455 kilohertz and amplified again. So at this point here, we would simply have a radio frequency carrier on 455 kilohertz being turned on and off in the pattern of the Morse code. So if our if our beat frequency oscillator was on 456 kilohertz, then the carrier on 455 kilohertz being switched on and off would mix with the 456 kilohertz BFO frequency to produce a 1000 hertz tone at the output. And the operator can make that tone anything he likes. If he's not happy with a 1000 hertz tone, he can adjust the BFO and make it an 800 hertz tone or a 500 hertz tone, whatever. It's up to that tone that you hear when you receive Morse code is generated by the product detector and the beat frequency oscillator. And it's simply the difference between the two. 455, the difference between 455 and 456 is 1 kilohertz or 1000 hertz. That's how we generate the tone in a telegraphy receiver, which is exactly the same as a single sideband receiver. The only difference is if you're really serious about Morse code telegraphy, the bandwidth of these IF amplifiers can be reduced even further to 200 hertz, because CW is the narrowest mode that we can have. We want narrow receivers because narrow receivers receive less noise. If you switch from double sideband on your radio to single sideband, you notice an immediate reduction in noise. If you switch from single sideband to CW and you have a CW filter fitted, you notice a massive reduction in noise. That's why CW is so good at communicating through difficult HF conditions, because the low noise in the receiver due to the receiver's very narrow bandwidth. There's another thing I want to talk about, and that's called automatic gain control. These receive amplifiers, these RF amplifiers, are very, very high gain and very, very sensitive. if a very strong signal is received, it's possible that the strength of that signal is so strong that it could drive either the RF amplifier or one of the IF amplifiers into becoming non-linear. And remember, all of the amplification done with single sideband must be, and double sideband must be linear, otherwise we get mixing. So a very strong signal coming down here could very well overload one of the IF amplifiers or the RF amplifier, and that would cause distortion in our speaker output. So we need a way of automatically controlling the gain of the receiver so that it can cope with strong signals and weak signals at the same time. For example, we might be talking to a radio amateur who lives 2 kilometres away, and at the same time we're communicating with someone from overseas. Well, when the chap that's 2 kilometres away transmits, he's got such a strong signal that he overloads your receiver and it sounds distorted. And that happens because you've turned up your receiver gain so high to hear the overseas station. Then the overseas station stops speaking, the local operator, it's his turn to talk, and your receiver is overloaded, and you have to adjust your receiver sensitivity to prevent that overload. Well, you don't want to have to do that all the time, so we have a feature built into our receivers called AGC, which stands for Automatic Gain Control, AGC. And the way AGC works is we take a little bit of the signal out of the RF amplifier, and it's a radio frequency signal, and we turn it into DC with a diode, and we add a little bit of filtering to the output of the diode, and that will produce a DC voltage here. And that, just in passing, that DC voltage would be connected to, could be connected to our S meter. So our S meter could work off the AGC voltage. Now, if the signal that's coming in is very, very strong, there will be more current passing through this diode, and the voltage here will be higher. It's only a small sample that we take out. We don't put a load or drain on the RF amplifier. We're just picking off a little bit of the signal, rectifying it, filtering it, and displaying it on an S meter so we know what the signal strength is. But we've now got a DC voltage here that's proportional to the received signal strength. So we can use that DC voltage to control the gain of, we could control the gain of the RF amplifier, and we could control the gain of both the IF amplifiers. We could either control the gain of both IF amps or the RF amp, or we could control the gain of all three. So this DC voltage, as it rises, because it's a very strong signal, it reduces the gain of the RF and IF amplifiers to prevent the receiver from being overloaded, which would sound like terrible distortion in the speaker. AGC normally has a couple of settings. If you look at your transceiver, you'll see there's AGC off, so you can turn it off. There's AGC slow, which means that it takes, if the AGC does turn the sensitivity of the receiver down, it stays down for maybe 2 or 3 seconds before it comes back to normal sensitivity. And we've got fast AGC, that is AGC that will operate quickly. If you're receiving Morse code, you really wouldn't want fast AGC, because the receiver would get confused about no signal and signal being present in the forms of didars all the time. So AGC can be turned off, it can be made fast, or it can be made slow. But automatic gain control, the function of it is to prevent our receiver amplifiers, the RF and IF amplifiers in particular, from being overloaded. It doesn't control the output volume of the speaker. It controls the RF gain of the receiver, which gives you a more constant volume output from your speaker, but it AGC is not applied to the AF amplifier. That's not an amplifier that's likely to get overloaded. The two IF amplifiers and the RF amplifier are the ones that are likely to get overloaded. SSB receivers, and I better write this in. I better write in that this is really a product detector. A product detector. Okay. When we adjust the BFO, we're only adjusting the receiver. We're not adjusting the transmit frequency at all. The transmitter is independent of the BFO. And for that reason, sometimes this control, or a control next to it, has got RIT written on it. And RIT stands for Receiver Incremental Tune. And what that allows us to do is to adjust the BFO so that we get the SSB or the telegraphy sounding just the way we like it without affecting our transmit frequency. Some people might like to hear the demodulated SSB a little bit deeper in tone than others. Others might like to have it higher. And if that control, if this BFO, if the RIT, the receiver incremental tune, modified the transmit frequency, then the other operator would be continually having to make adjustments. Whenever he transmits, you have a fiddle and change your frequency. You transmit, he has to fiddle and change his frequency. He transmits and you fiddle, and so on. How irritating. So we have on our receivers a RIT, receiver incremental tune, and it only adjusts the receive frequency and doesn't affect the transmit section of the radio at all, so that the two radio emitters are not doing what's called walking up or down the band, following each other, moving 300 or 400 hertz every over and wandering kilohertz in frequency off the frequency they started on. That's the function of receiver incremental tune, and you do need to know that one. Rightio, we're going to have a look shortly at the block diagram of the transceiver and see if we can bring all of this together a little bit for you. This is just a little add-on that I'm doing for the standard course, because you won't be asked. The block diagrams that I've shown you are the ones you need to know. When I show you the transceiver block diagram, you don't need to know it. But it's so good to have one diagram with almost everything on it for double sideband and SSB for you to revise what you've learned in these tutorials. So I'll see you again shortly, and let's have a look at that block diagram. This slide is the block diagram of a practical SSB receiver, and I think that frequency is wrong up there. I think it's supposed to be 29 megahertz. Doesn't really matter. It's 29 to 29.5, and I've got 28 to 28.5. Okay, let's just look at the receiver. We looked at this is a single sideband transceiver. This is the transmitter section, obviously with a microphone, and the lower section is the receiver, and there are some common stages, oscillators in particular, and a filter, common stages between both the transmitter and the receiver. Let me just clear that rubbish up. Suppose we have a signal coming in here on 29 megahertz down the antenna. This is a changeover relay. When you push the push to talk on your button, either a mechanical relay, electromechanical relay, or an electronic relay operates and connects the antenna to either the transmitter during transmit or to the receiver during receive. So we have an SSB signal coming into the antenna, picked up by the antenna, goes to a receive amplifier, two receive amplifiers. So all they're really doing is making that signal much, much stronger. We've got AGC voltage controlling the gain of the first IF amplifier in the receiver. So we come in on roughly 29 megahertz, and the first oscillator which is used in both the transmitter and the receiver. This frequency converter here in our receiver converts our incoming signal on 29 megahertz to our first IF frequency of 21 megahertz. So we're not going to have any image problems with a 21 megahertz first IF. Then coming out of the first IF, we have a single sideband signal on 21 megahertz. Then we use a frequency changer again, another frequency changer, to convert our 21 megahertz Ssb signal to a 7 megahertz Ssb signal. The difference between 14 and 21 is 7 megahertz, and so on. We're taking advantage of the very good crystal filter we've got in our transmitter to improve the selectivity of our receiver. That's a crystal filter. That's the symbol for a bandpass. And so we're routing our receive signal through the same sideband filter that we used on transmit. And that gives us more selectivity by using that very highly selective filter. So up till this point here, we haven't done much to the signal at all except amplified it and changed its frequency. At this point, at the output of that crystal filter, we've got the same signal that we had on 29 megahertz. It's the same bandwidth. It's just now on 7 megahertz, which is our last IF frequency. There, 7 megahertz. Then we go into our product detector, and our carrier oscillator is on 7 megahertz. So the difference between our carrier oscillator and our 7 megahertz Ssb signal is going to be our audio, our converted audio from our upper or lower sideband. That's all pretty easy once you get the hang of it. I'm going to go through it quickly once more. You don't have to know this block diagram, but it is good to look at. And do read the controls down here, because they tell you where the controls would be on your transceiver for the different things. For example, I think there's RF gain control there, not shift, AF gain would be in the audio amplifier, and so on. I don't want to spend too much time on that. So a 29 megahertz signal comes in. It could be any frequency. It's amplified again. We're detecting some AGC voltage there to control the gain of the first IF amplifier. The 29 megahertz signal goes into a mixer, a frequency converter, and that frequency converter, see the PLL there on 8 to 8.5 megahertz, that will convert our Ssb signal to 21 megahertz. Then we use another mixer, frequency converter, and that converts our Ssb signal to 7 megahertz. We take the benefits of the crystal filter that we used in the transmitter, gives us more selectivity. Our 7 megahertz signal goes into a product detector, along with roughly 7 megahertz from the carrier oscillator, and the difference between the carrier oscillator and that 7 megahertz is our audio in the output. It's really as easy as that. And I'm just going to go through the transmitter again with you. Sorry, the transmitter. We have the microphone amplifier. It goes into the balance modulator with the carrier oscillator, and that at that point there, that gives us a 7 megahertz Ssb signal, because the carrier oscillator is on roughly 7 megahertz. We then go through a sideband filter, crystal filter, which removes the sideband we don't want. We have 2 carrier frequencies so that we can position the sideband that we want to go through the sideband filter. The first IF amplifier is amplifying 7 megahertz. We then go to a frequency changer and change the Ssb signal to 21 megahertz, but it's still an Ssb signal. It's just been moved in frequency to 21 megahertz. We then go into another mixer, another frequency changer, VFO, which is a PLL VFO, and that lifts the 21 megahertz up to 29 to 29.5, depending on what frequency our VFO is on. And after that, it's simply amplification, 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 and up the antenna we go. There is something I haven't spoken about, and I'm not sure that I have to, but I will. That's automatic level control. Automatic level control is to a transmitter what AGC is to a receiver. Automatic level control prevents these amplifiers from being driven into non-linearity. If they become non-linear, we're going to cause splatter. And how that could happen is if the operator wound up his microphone gain too high, or he used a power microphone. If the microphone gain goes too high, because on an SSB transmitter, the power output is controlled by the microphone gain. If you turn your microphone gain right down to nothing and talk into the microphone, you won't transmit anything. If you turn your microphone gain up, you begin to transmit more and more power. And some operators think, okay, more power is good, so I'll turn the microphone gain all the way up. In fact, I'll even build another amplifier and amplify the microphone even further. The problem with that is you're going to overdrive these amplifiers, these RF amplifiers, pre-driver, driver and power amplifier. They're going to become non-linear, and you're going to create splatter and interference to other operators. What the ALC does, it measures how much power is being transmitted, takes a little bit of out. There's a rectifier in it and a little filter capacitor, which just takes some of it. That's an earth. Don't have much room to draw an earth in there. We take a little bit of our output power, rectify it, filter it, turn it into DC, and use that DC to control the gain of that stage. And that prevents us from over-modulating. That's what ALC is. AGC, on the other hand, prevents the receive amplifiers from being overloaded by strong signals. ALC prevents the transmitter's power amplifiers from being overloaded by a silly radio operator turning his mic gain up too far. Well, that's about it. I think you're pretty well done on single sideband. We're going to run through the question set next, and if I have forgotten, I will see that in the question sets, and I'll cover it as I go. But I think we've done a pretty good coverage, so thank you for being patient and listening to me and watching, and let's have a go at those questions now. Okay, welcome back. Let's have a look at some of the types of trial questions that you could, the types of exam questions you could get in your assessment. These are just facsimiles of the real exam questions, but they're very representative of what you might get in the exam. So we're going to do section 18 on receivers. And you should have watched tutorials 23 and 24, and your self-test for this is drill 18. 18.1. The ability of a communications receiver to distinguish between signals that are close in frequency is known as selectivity. I won't talk a lot about these. I think we've covered them pretty well. If I think I can add some more information, I'll do that. 18.2. A receiver which cannot separate a number of stations on adjacent frequencies, that's nearby transmitters not very far away in frequency, that is a property called selectivity. Selectivity is the ability of a receiver to receive the desired station and reject other stations that are close by in frequency. 18.3. The ability of a communications receiver to pick up weak signals is known as sensitivity. It's your S meter reading, and the sensitivity of a receiver is measured in microvolts. 18.4. A receiver that cannot pick up weak signals is lacking in sensitivity. 18.5. In an AM receiver, demodulation normally takes place in the detector, and the detector could also be called the demodulator. And this is talking about double sideband. When they say AM, they mean double sideband. If it was single sideband, the name of the demodulator would be product detector. I'm sure we'll get a question on that shortly. 18.6. A detector in a communications receiver can also be called a demodulator. 18.7. All radio receivers must have a detector. If you don't have a detector, you don't have a radio receiver. You can't hear what you're picking up. So every radio receiver, no matter what type, needs a detector. The detector in a double sideband receiver is just called a detector or demodulator. In an Ssb receiver, the detector is called a product detector. To make a Morse code signal audible, or to make Morse code audible, a receiver has a beat frequency oscillator, the output which is normally fed to the product detector, not the detector stage. Oh, the detector stage, yes, that is it. I was expecting them to say product detector, because the product detector is used for both SSB and telegraphy or Morse code reception. Should remember that. 18.9. In a receiver, to receive telegraphy transmission efficiently, a beat frequency oscillator is employed too. Remember we talked about the the telegraphy receiver, and that Morse code doesn't make any sound. It's the beating of the BFO with the CW signal from the last IF stage. It's when you put your BFO signal against that you actually get an audio difference, which is the audio signal for the SSB receiver. In other words, the Morse code tone is created in the receiver. Morse code has no tone. It's just a radio frequency wave being turned on and off. So it has no tone. So if you didn't have a BFO, all you would see is the S meter flicking up and down. You wouldn't hear any tones, and you'd just hear clicks or thuds in the speaker as the carrier was being turned off. If the last IF is 455 kilohertz and your BFO is on 456 kilohertz, then the difference is 1000 kilohertz, and you're going to hear the Morse code tone. 18.10. To enable an AM receiver to resolve CW signals, it is necessary to include a beat frequency oscillator. Not so hard. 18.11. In a single sideband receiver, a product detector is normally placed between the IF amplifier and the audio stage. And you would just look at the block diagram, and if you become familiar with your block diagram, you'll be able to answer any of those questions. 18.12. A product detector is a mixing device used for the detection of SSB and CW signals. 18.13. A product detector is best suited for the reception of single sideband suppressed carrier transmission, and it's also useful for telegraphy as well. 18.14. The output of a product detector stage consists of audio frequencies. So the output of the product detector in an SSB or telegraphy transmitter would go to the audio amplifier, and from there it would drive a loudspeaker. 18.5. The detection of SSB signals is normally performed by actually there's two answers here. Product detector is the correct answer, but you also need a BFO. But that is the most correct answer. So for SSB you need a product detector and a BFO. But if you had to choose one between product detector and BFO, you choose product detector. Product detector has to have a BFO, so I suppose A is arguably the correct answer there, and the only correct answer. 1816, a detector commonly used for the reception of single sideband signals is a product detector. You can see the theme here, can't you? They really want you to know about that product detector. 18.17, one of the main functions of the RF amplifier in a superheterodyne receiver is to improve image rejection. Remember the first RF amplifier on the receiver? Remember we said that it is a broadband amplifier, but it's not really broadband. It just the RF amplifier in a receiver can receive the entire band that you're operating on. So the bandwidth of a RF amplifier in a receiver might be 200 or 300 kilohertz. However, the image, if the first IF is a high IF, say 10.7 megahertz, then the image frequency is going to be a long way out of the passband of the RF amplifier, so the RF amplifier is going to help reject that image interference. Not sure? Go back and look at the tutorial again. 1818. The stage in a superheterodyne receiver adjusted to change the tune frequency is the local oscillator. 1819. The IF amplifier in a superheterodyne receiver operates at a fixed frequency only. It doesn't operate, it really operates over a narrow band of frequencies. That's a correct answer. But it operates over a narrow band because it might have to pass single sideband, which is 3 kilohertz, double sideband, which is 6 kilohertz. So it has bandwidth. It's not just a single frequency. It's usually plus or minus 1.5 kilohertz, which is 3 kilohertz for Ssb, and 6 kilohertz for double sideband. 1820. A superheterodyne receiver is tuned to receive 355 kilohertz. If its local oscillator is in 4010 kilohertz, the intermediate frequency is. Well, the intermediate frequency would have to be the difference between the local oscillator and the received signal. And the difference between the local oscillator on 4010 and the received signal on 355 is 455 kilohertz. So the IF in this receiver would be 455 kilohertz. Question 1821. In this diagram, the frequency of the IF amplifier stage, this stage here, is what? Well, they've shown you an incoming signal of 355 kilohertz. The local oscillator is the IF frequency higher than that. So the difference between these two frequencies is the intermediate frequency. So if we subtract 3,555 kilohertz from 4010 kilohertz, we get, need a marker, we get 455 kilohertz. 1822, with an increase in signal strength, a receiver's AGC, that's automatic gain control, if the signal gets really, really strong, the AGC will reduce the receiver gain. And the stages that it operates on are the RF and IF amplifiers. Just a little bit of added revision there. 1823. The purpose of AGC in a superheterodyne receiver is to maintain a constant output level with variation in input signal. So if you get a really weak signal and the audio and the signal strength drops right down, the AGC increases the gain of the RF and IF amplifiers to give you a stronger signal. 1824, AGC in a superheterodyne receiver is usually applied to the RF and the IF stages. Question 1825. In a superheterodyne receiver with an IF of 455 kilohertz is tuned to receive a signal on 3610 kilohertz. The local oscillator frequency will be 455 kilohertz higher than the received signal. And don't forget to use a calculator when you do these things in the exam, because it's quite easy to make a mistake. I don't have to use it, but I'm just reminding you that if you're silly to make an arithmetic error when you know how to do something. So all we need to get to the answer to this is to add that, and we can do that in our head, but if you're not sure, 3610 plus 455 equals 4065 kilohertz. And we simply, the local oscillator, whatever the IF is, the first IF, the local oscillator, is on a frequency above the received signal as a rule. It could be below, but it's general practice to have the local oscillator above the received frequency, and it's above it by the amount equal to the intermediate frequency. Question 1826, if a superheterodyne receiver with an IF of 455 kHz is tuned to receive a signal on 3600 kHz, the local oscillator may be on 3600 plus 455, and that's going to be, I could use a calculator, but that's going to be 4055 kHz. Should check it for you. (3,600) plus 455 equals 4055 kilohertz. 1827. If a superheterodyne receiver with an IF of 455 kilohertz is tuned to receive a signal on 3555 kilohertz, the local oscillator will be, the local oscillator is going to be higher than the received signal by an amount equal to 455 kilohertz. So we simply need to go, just going to clear my calculator, 3555 plus 455 equals 4010 kilohertz. So the answer is C. 1828. The frequency of the local oscillator in this block diagram. Okay, the received signal is 355 kilohertz and the IF is 455. So the local oscillator must be higher than the received frequency by 455 kilohertz, and I think that's 4010 kilohertz, but I'll double check it. We're simply going to go clear 3555 plus 455 equals, and it's 4010 kilohertz. Use a calculator. It can save you making a simple arithmetic error which is going to cost you 2 marks in the assessment. 1829. If a superheterodyne receiver is tuned to 3600 kilohertz and the intermediate frequency is 455 kilohertz, the local oscillator will be on 3600 plus 455, which is 4055 kilohertz. Question 1830, you'll be getting sick of these, but it's good to have as much practice as you can possibly get. A superheterodyne receiver is tuned to 1100 kilohertz. The intermediate frequency is 455 kilohertz. The frequency of the local oscillator will be 455 kilohertz above the frequency of the received signal. So it's clear 1100, we can do it in our head, but let's be safe, plus 455 equals 1555 kilohertz. 1831. An AF amplifier is designed to amplify within a frequency range of about, well, they're audio frequencies, and that's an audio frequency range 15 to 20,000 hertz. However, in communications, in amateur radio communications, we normally restrict our receive signal to our modulating audio to 0 to 3 kilohertz. So we don't use all that audio bandwidth. If we did in amateur radio, the bandwidth of our signals would be too wide. 1832, this block diagram represents a, let's have a look at RF amplifier. It's got a detector, not a product detector, so it's an AM receiver. It's got 2 frequency converters and 2 IF stages. So that makes it a double conversion receiver, and its proper name is a double conversion superheterodyne receiver. 1833, a double conversion superheterodyne receivers use 2 intermediate frequencies. 1834, a double conversion superheterodyne receivers can receive only one mode. Note, provide a high attenuation of image interference. Double conversion receivers do that because their first IF is a high frequency, typically 10.7 or 16 megahertz. All of those IF frequencies are guarded. No one is allowed to transmit on them, because they'd interfere with all receivers if they did that had that IF frequency. 1835, a single conversion receiver has 1 intermediate frequency. 1836, a single conversion superheterodyne tongue twister. Single conversion superheterodyne receivers use only 1 intermediate frequency. Double conversion use 2, triple conversion use 3. 1837, this block diagram represents, that should be detector. I'm not going to change that, it's a simple error. I'll change it on your sheet copy. But that I just noticed that should be the detector. It should be RF amplifier, mixer local oscillator, first IF, detector, and then audio frequency amplifier. So that's an error there, chaps. Guys, don't get on to me too much about that, because it'll be okay in your drill software. But that is, without any doubt, even if that wasn't labelled, even if there weren't any labels on this at all, you should be able to tell this is a single conversion receiver, because it has only 1 frequency converter in it. This one, the mixer and local oscillator, perform the same combined function of a frequency converter. 1838, in a direct conversion receiver tuned to receive lower sideband signal, the oscillator frequency is, so if we want to receive the lower sideband, the oscillator would have to be on the slightly above the upper frequency of the upper sideband, so slightly exactly the same frequency as the suppressed carrier. There you go. So to receive single sideband, you need to put the BFO, they've just called it an oscillator here. Oh no, it's not the BFO, it is an oscillator. You need to put it on the suppressed carrier frequency, because in single sideband you don't have the carrier. It was suppressed in the balance modulator in the transmitter. Question 1839. The process of mixing audio and RF voltage is called modulation. 1840. The operation of a receiver incremental tuning, clarifier or RIT control in an Ssb receiver provides a small variation in receiver tuning without changing your transmitter frequency. 1841. The receiver incremental tune, clarifier or RIT, RIT is the preferred word, of an Ssb receiver allows adjustments of the receive frequency without changing the transmit frequency. How many we got left here? We've got a couple left. Just going to do a page down so I can get this all on one page. 1842. The block diagram that is not identified in this diagram is every radio receiver needs a detector, and this is a double sideband receiver, single conversion, and this radio receiver does not have a detector, which would go just before the AF amplifier, the audio frequency amplifier. 1843, in this simplified block diagram, the unidentified section is the BFO, the beat frequency oscillator, goes into the product detector. So this single conversion receiver is capable of receiving, because it has a product detector and a BFO, it's capable of receiving single sideband and telegraphy. 1844, in this simplified block diagram of a telegraphy receiver, it's also an Ssb receiver, the unidentified section, I'm looking for an unidentified, oh, there's the unidentified section. It's the local oscillator. I was looking for something that was unidentified. The sine wave on the symbol tells you that is an oscillator. It's just not labelled as a local oscillator. There are two oscillators, the local oscillator and the beat frequency oscillator. The first oscillator is called the local oscillator. Called local oscillator because it's originally was the oscillator that put the carrier back in, but now we have multiple oscillators and receivers. 1845, what does the term receiver overload? Well, receiver overload is strong signals potentially driving the RF amplifiers in your receiver into non-linearity, and if you do, that produces distortion. So let's have a look what could be the answer. Not A, interference caused by a strong signal from a nearby transmitter is the answer. B. Well, that's it. That's the end of the set. Thank you for your time and your efforts. I'll meet you back in the next tutorial, and don't forget you can test yourself with drill number 18 on this subject, and you can go back and look at the video tutorials as often as you want to. Hope your study goes well. Please email me if you need assistance, ron@res.net.au. Good luck with your studies, and I hope it's been pleasurable for you. Cheers for now. I'll catch you soon.